Lesson 0.1 Measurements and Significant Digits. In Physics 20, we're going to be using a great deal of measurements. So the biggest difference between physics and math is the numbers that we're using are measurements. Measurements always involve uncertainty, and uncertainties in measurement cannot be avoided. For example, the length of a measuring tape, which is primarily used to measure distance, will change with temperature, which means the distance you will measure will change depending on the temperature of the room you're measuring the object. In experiments, this measurement uncertainty, the unavoidable inaccuracy that we find in our measurements, is called error, or sometimes experimental error. It's important that you realize that error is not a mistake. Some students will often blame themselves, human error, for the inaccuracy in their experiments. Error is not a mistake. You can't have experimental error by miscalculating something. It's just an unavoidable inaccuracy. Due to the limitations of the equipment we're using. It is impossible to have a perfectly precise measuring device, and for that reason, it's impossible to have an experiment without some experimental error. There will always be uncertainty in our measurements. We can actually calculate the amount of error in an experiment using the formula for experimental error, or percent error. The formula for percent error is percent error equals measured value, which is the value in the experiment that we've measured that might have some uncertainty, minus the predicted or the expected value, divided by the same predicted value, times 100% to turn it into a percentage. Another important concept that you need to understand measurements is the concept of precision. Precision is limited by how many accurate decimal places a measurement has. For an example, 100 meters is less precise than 100.2 meters. This is because 100.2 meters has an extra decimal place. It has more decimal places, therefore it's more precise. In experiments, we'll use a variety of different measuring scales. For example, we might use a scale to measure mass or a ruler to measure distance. Precision is given by the smallest division on the measuring scale we're using. For example, millimeters is the smallest division on a meter stick. Therefore, the meter stick's precision is limited to the millimeter. Significant digits. Significant digits are very closely related to measurements and measurement uncertainty. For example, if we have a box and we want to measure the width of the box, we'd line it up next to a ruler and we'd examine the measurements along the side of the ruler that the box lines up with. In this picture, the box doesn't line up with the 3 or the 4, it lines up right between the 3 and the 4. We can't know exactly where it is because that's our smallest measurement, but we can estimate that it's about 3.5 centimeters. The 3 represents a digit we are certain of. We're certain that the 3 is accurate because the box definitely goes past 3 but not quite to 4. We're not so certain about the 0.5. It could be 0.4, it could be 0.3, it could be 0.6. We're less certain about that one, or we'd say it's an uncertain digit. The significant digits in a measurement are all of the certain digits from a measurement plus one uncertain or estimated digit. To be able to use measurements in calculations, we need to be able to count how many significant digits a measurement has. The rule for counting significant digits, or SIGDIGs, is find the first non-zero number in the measurement, count it as significant, and all the digits to the right of it, including zeros. As significant. For example, four numbers: 123, 0.123, 0.002 or 123, and 0.203. The first non-zero digit in 123 is the 1. The digits that follow are significant, so it has 3 significant digits. In 0.123, the 1 is the first non-zero number. The digits that follow are also significant, so it has 3. In 0.00123, we also have 3 significant digits. In 0.203, the 0 in the middle counts because it follows a non-zero digit. And it has 3 significant digits as well. We use the counting rules for significant digits to do calculations with measured data. There are 4 rules you need to know for doing calculations with measurements. The first rule is the adding-subtracting rule, which has to do with the precision of the measurements that you're adding or subtracting. When adding or subtracting two measured values, round the calculated answer to the same precision as the least precise number. For example, when we plug the numbers 1.2 or 12.3 plus 0.12 plus 12.34 into our calculator, we get the answer 24.76. But this isn't correct rounding. To get correct rounding, we find the precision of each number. 12.3 has only 1 decimal place precision. (0.12) has 2 decimal places precision. And 12.34 also has 2 decimal place precision. For this reason, 12.3 is the least precise. It only has 1 decimal place, and our answer should only have 1 decimal place as well. 24.76 rounds to 24.8 because the 6 bumps the 7 up to an 8 when we take it off. Second rule is the multiplication and division rule for measured data. When multiplying or dividing, you can round the calculated answer to the least number of significant digits. Or the fewest amount of significant digits in the data you are multiplying or dividing. For example, 1.23 times 54.321 in our calculator gives us quite a few decimal places, 66.81483. But this is too many decimal places. We need to round it. We look at our original data. 1.23 has 3 sig digs. 54.321 has 5 sig digs. 3 sig digs is the fewest amount, so our answer should have only 3 sig digs, which means the answer is 66.8 once it's rounded. The third rule is for doing a series of calculations. These calculations could involve multiplication, division, addition, or subtraction, just as long as there's many calculations in a row. When doing a series of calculations, do not round until the end. This is really important. You can introduce rounding error into your calculations if you round too early, and your answer will be wrong. So do not round until the end. At the very end, you can round the final answer to the smallest amount of sig digs you can see in the original data. The fourth and final rule involves exact numbers. These are numbers that you read off a data sheet, or numbers that are generally accepted, or numbers that just when you count things, they don't have halves or decimal places, they are what they are. So when calculations involve exact numbers, do not count their sig digs. Consider these exact numbers to be infinitely precise. They're perfectly precise. They don't need to be considered towards our rounding rules. For example, 12 eggs is an exact number. You don't have 12.5 eggs, you have 12 eggs, and we're pretty certain about that. Times 52.39 grams per egg gives us a number, 628.68 grams. To round this answer, we look at our original numbers, but we don't look at the 12 because it's an exact number. Don't count these significant digits. The 52.39 is a measured number. It's not exact. It has 4 sig digs, so our answer should have 4 sig digs. This means 628.68 rounds to only be 628.7 because the 8 bumps the 6 up to 7 when it rounds.